Alright, I'm Zack, and that's my lab partner behind the camera, Loni. Here's our circuit. So basically it's a lightning and thunder detector now. We upped the game a little bit, so we put two circuits next to each other. We got our lightning detector from the last one that's hooked up to the lab jack. And then we have our microphone circuit on the right side. This will pick up the sound of the thunder, and the goal is to eventually design a program that will, using an equation, tell how far, what the distance of the lightning bolt was away from where you're standing or where the circuit is. We're going to run it, show you a little bit what's going on. So we're going to use YouTube for the thunder sounds. Yeah, so let's just try it. Let's go. Alright, so here it is. Picking up the thunder sound, some flashes of lightning. You hear a couple more thunderstrucks. Alright, so then we're going to click this self-destruct circuit, which really is just to stop it. And you'll see on our graphs, our bottom graphs record the exact amount of time. So we ran it for about 27.5 seconds. I'm going to go through just tell you exactly what the graphs are doing in all of these. So these again are just like a live streaming of whatever's going on when we're running the program. We're really just using these for reference so that we can kind of see is our circuit making noise on this when something comes into the microphone or when something comes into the solar cell. The bottom graphs are what matter, because when we stop the program, this records and stores all our data that ran while the program was running, and it'll just put it all on two time axes that match each other. So you got lightning on this side and thunder on the right, and you can see that the times match perfectly, so that we can see, okay, so this struck here, there's a lightning flash here, and then thunder was over here. Looks like there was 5 seconds in between or something like that, and then we can use that to change or to measure where the lightning bolt took place. So it's kind of cool how that worked out. Again, our meters in the middle are just kind of for fun. We have intensity values up there. Our button down here has synchronized to where when we press it, it actually stops both graphs from working. So you'll see that in our block diagram. But that's pretty much what our interface looks like, our front panel on our lab view, and what's measuring from our circuit.
Okay, so this is the block diagram of our LabVIEW program. We have right here our lab jack, and this is where our circuit is outputting into the lab jack. We're running our data into a waveform, these two right here. This top one's the lightning, this bottom one is the thunder. And before our data gets inputted into these waveform graphs, we had to add two equations. This like 5 minus x and this 0.5 minus x, and basically we just had to add those because our data on our graphs were inverted. It was like upside down. So we thought it would be more appropriate if they were going up when the intensity increased. So that's why we added these two little things. And then we also right here we have a wait clock, and we have it set at 30 milliseconds, which means that each little data point on the graph is taken every 30 milliseconds, and that's what keeps track of our time. And then right here we have numeric indicators, and that just wherever like the y value of the graph is, it'll just give a numeric indicator like on the side of our graph if you ever want to like reference it. And then we added these two components for fun. This is our meter, which goes up with brightness, and then this is our water tank, and that goes up when the sound goes up. And then since these two circuits are in the same while loop, it synchronizes all the graphs together, and we have one stop button down here, so that stop button makes every part of this stop. And then outside of our while loop, we have two bundles, and feeding into like our grid graph, and this graph is what we use to keep like the real time and the real recordings of our data. And these two bundles just kind of help set the like time axis, and we have our data from the live waveform going into it, and we have where the x value starts at and the time delay in between every recording, and that goes into this more like fancy graph. And we just had the same thing going in for both our lightning strike graph and our thunderbird graph. That's it. We're about to show you the schematics of our new circuit on the scroll. First, we have our light detector, which, if you watch the prequel, you can get more details about it. This is just our updated one.
We took out the
buzzer
and replaced it with a
resistor.
Because, yeah, we'll explain in a second.
And then what we added to our new circuit is the sound detecting element. And that big like donut is actually a microphone. And then we just use an op amp to amplify the signal. And then we have our LED light that flashes when it detects sound. And then both components of this circuit are being inputted into the lab jack. Inputted into the computer. And you can see
we got the lab jack here.
Yeah, and that is for the lightning, and that's for the thunder. And lightning and thunder detection circuit for our thunderstorm. We encountered some technical difficulties when adding the microphone component to our circuit. Zach, do you want to explain what that was?
Yeah, so, we thought, okay, so solar cell, you're going to want light to come in, and then you want an audible sound because you don't want to, like, light up an LED with a light source because that would totally counteract each other. So we're like, all right, buzzer when light comes in, cool. And then next to it, when we want to detect thunder, we're going to have a microphone, which will, occur a few seconds later, and it'll pick it up, and then it'll flash an LED, so you, like, sound makes light makes sound. Well, the thing we didn't anticipate was the fact that when the lightning flashes and sets off the buzzer, the microphone picks up the buzzer and sets off our LED. So it totally ruined the entire point of our circuit. So we took out the buzzer and we just plugged our lab jack straight in, put a resistor instead of the buzzer, and just ran it straight into our computer lab jack interface. So the only time you ever see the flash make a difference is
on our intensity graph. Versus time.
Right.
What did we learn when making this?
Okay, so we learned a couple things. We learned about how to make a microphone circuit because we finally put a microphone into our design so that we could pick up sound. So that was kind of cool. It works like a like a resistor, and so we kind of turned it into like a voltage divider, as you can probably see in our schematics. But it was cool how it worked. Sent a voltage through the circuit. We picked it up on our lab jack. So that was the first thing.
And then we learned how to incorporate the lab jack into our circuit in order for our circuit to input into the computer and record our data through that. And then along the lines of learning the lab jack, we learned how to
work with LabVIEW, which is kind of cool.
Yes.
First experience of LabVIEW. So it was cool to like interface, be able to pull up graphs and use the programming of LabVIEW, which is kind of cool. It's more of a picture. It's pyramid. So we just use the interfacing, put up a few graphs, be able to take data from our circuit and put it on a computer and have them interact with each other and speak to each other. So that was really cool.
And then lastly, we learned that we have to be careful in picking out what we're going to use as our like sensory detectors and the sensory alarms.
Yeah.
And that they don't clash with each other.
Don't use a buzzer next to a microphone because that totally defeats the purpose. So, lesson learned. Easy. So, where are we going?
I'm hungry.
Oh, let's go
to the app.